Okay, Assalamualaikum warahmatullahi wabarakatuh. As promised in class, I'm going to show you an example of how to plot root locus utilizing all the 9 steps that we have done for the previous classes. Okay, I've shown you steps 1 until step 6. So I'm going to show you now steps 9 on this. Okay, so this is a past year questions where you have a control system and then you need to plot the root locus. Okay, you need to plot the graphs. Okay, so how are we going to then plot using this? So you have a system where you have a controller K, and then the transfer function of a system is 1 over s plus 2, s plus 6. Okay, so what we're going to do then, we're going to plot the graphs, okay, by use the root locus graph using all the 9 steps. So K is your transfer function of controller, and this is a transfer function of your GS is a transfer function of your system. Okay, so in this case you have a feedback, and the feedback is a negative feedback with magnitude of 1. I'm not going to write there. Okay, so it's just a negative feedback there. All right. Okay, then from here what you're going to do is you're going to plot the graph using, you're going to start with the open loop transfer function. So what is open loop transfer function? It is your KGH, isn't it? So you're going to have to multiply for step 1. You're going to multiply your K multiplied by G multiplied by H. Okay, so that's going to be K over S plus 2, S plus 6, and then multiply by 1. I'm not going to write 1, of course, right? So that is your open loop transfer function. So when we look at the numerator of your open loop transfer function, equate the numerator to 0. In this case, you have non-zero system because you don't have roots. Okay, so there's no root. When there's no roots, it means there will be no 0. Okay, it will have roots if I have ks there, but in this case just k. Okay, so I don't have roots. If I have s, means I have a root with value of s equals to 0, but in this case there's no s there, so there's no root, so there's no 0. Okay, right, then you do for your denominator, you have denominator s equal with 0, so you're going to have s is equals to 0, s is equals to minus 2, and s equals to minus 1. These are minus 6, sorry, these are all your poles. Okay, so you're going to have poles, 3 poles. So the first pole is 0, second pole is minus 2, third pole is minus 6. Okay, and the magnitude of your, so the number of your poles is P. I use denominator representation of P. P is equals to 3. Okay, so there are 3 poles. Basically, class, this is the same thing. If I was given poles, I can use also poles and 0 to come up with transfer function of my system. Okay, it's the same thing. If I do the other way around, the opposite, I will have using my poles and 0, I can then have the transfer function of the system. Then the next one is I need to plot the graph. Not plot but sketch. Okay, so when I do the sketching, I'll just sketch nicely, but when you already completed all your steps, you actually need to plot this graph on your graph paper. So normally in exam or test, you're going to be given, or you will need to provide your own graph paper. You need to use your graph paper to plot your root locus. So you cannot just sketch. You can sketch when you're doing it, but then you need to plot it nicely on a graph paper later on. Okay, so if you look at when you do the plotting, you must make sure the scale for your imaginary and your real axis, the scale must be the same. So if I use 1 cm is equivalent to 1 magnitude of 1 for imaginary axis. So similarly for my real axis, I have to do the same. Why? Because you later need to plot this and you need to measure the angle. If you measure the angle, you need to use your protector and all, isn't it? So then the scale must be the same. Okay, so you cannot use different scale. For example, imaginary axis using 5 centimeter equals to 1 unit, but for real axis 1 unit is equal to 1 centimeter. That will not give you the accurate scale. Okay, for poles, I'm going to use cross like before. So for 0, I'm going to use circle, but I don't have 0 here, so just have 3 poles. All right, so this is step number 1. For step number 2, I just need to determine which is the location of 0. So this one, the first one is actually my odd number. So to the left of odd, there will be locus there. The second element here is actually even, so that to the left of even there will be no locus, isn't it? Okay, so to the left of even there will be no locus. The third element here is my odd, so to the left of odd I will have another locus, and this is going towards infinity because I don't have other element at the end of that locations. So this is for step number 2. So you can just write there, step number 2 is region of locus, and you already know in your mind that you're going to have 2 region of locus from pole number 1 until pole number 2, and then in between 2 and 3, the pole 2 and pole 3, there's no sketching, no locus, and then from pole 3 to the infinity there will be locus. Okay, so this is your step number 2. Then for step number 3, I can just I can write down, step number 3, I can write down that there are 3 locus. Why do I know there's 3 locus? Because there are 3 poles. So there will be, because poles are the starting point of your locus. So definitely you have 3 poles, means you're going to have 3 locus. Starting at your poles and ending at 0. But since I do not have any 0, so there's no locus ending at any 0. If I have let's say 1 0, that means I have 1 pole that will go to 1 0 and the other 2 will go to plus minus infinity. Or if I have 2 0, then means there will be 2 locus that will end at 2 0 and the other one will go at infinity. But because I do not have 0 at all, so means to say all 3 locus will end, will start from my open loop poles and it will end at my 3 zeros, as 3 plus minus infinity, okay, because I don't have any 0. Okay, so these are all going to end at plus minus infinity. Next is step number 4, because I know that there are 3 zeros that will go to plus 3 poles that will go to plus minus infinity. I need to find the angle of asymptote. How do they going? Are they going to the plus minus infinity? So if you remember the formula, 2k plus 1 multiplied by 180 degrees divided by p minus z, and the value of p minus z is your number of poles minus number of 0. So in this case, you have 3 poles, you do not have 0, so that is 3 minus 3 minus 0 is going to be 3, isn't it? So because you have 3 poles and you have no 0, so that is going to be divided by 3 only, 3 minus 0, okay? So that will be 2k plus 1 multiplied by 180 degrees divided by 3. So that is 60 degrees, 60 degrees, 180 degrees, and 300 degree. Okay, so if you have that is actually for k equals to 0, k equals to 1, and k equals to 3. Okay, k equals to 2. If you have k equals to 3, then the value will repeat 60 degrees. So that is not going to be, no need to do anything after that. Right, so this is depending on the value of your p minus z. If your p minus z is equals to 2, then you have only 2 angle, 90 degrees and 270. If your p minus z is equals to 4, you're going to have 4 angles. So because it depend on the value of your p minus z as well. Okay, the moment you have find out the angle of asymptote, you need to sketch them. The angle will be calculated from horizontal counterclockwise, so that will be 60, that will be 180, and the other one is 300 degree. Okay, this is just a sketch, but in your case, you need to use your protractor to find out later on. Then the next step is we want to find out where to place this asymptote. This one we know already the how the angle looks like, but we want to know where to place this asymptote on your sketch. So if I want to, next one I want to do is I want to find out if I already have this asymptote, where to place it. Okay, so the point where I want to place the asymptote is actually step number 5. Okay, so we need to then identify our step number 5, okay, to find out the position for our asymptote. Okay, so the position or the location of our asymptote is alpha A. So if you remember the formula, some value of poles minus some value of 0 divided by p minus z. So I'm going to put the value of poles, so that will be minus my some value of my 0, which I don't have anything, so that would be just 0, divided by 3, because my p minus z is equals to 3. Okay, so that will be 0 plus negative 2, okay, plus negative 6. Divide by 3, Okay, there's no value of 0, so that is why I put 0 there. You don't even have to put there lah. If you know already that will be 0, isn't it? Divide by 3, that will give us negative 8 over 3. So that is equivalent to minus 2.66. So the moment I already know the location of my angle of asymptote, I can take that angle of asymptote. Of course, I need to measure it correctly, the magnitude and all. And I need to place that angle of asymptote at negative 2.66. Okay, so that will be where I'm going to put my angle of asymptote. Okay, so now we already have three asymptotes. One is 60 degrees, one is 180 degrees, and the other one is 300 degree. So the position of the asymptote is at negative 2.66. So then we can tell from looking at our poles and also a region of our locus, we can tell that our locus will be within that. Okay, so between the two poles, there will be one locus going towards each other. Okay, there are two locus that will go from that point to that point. Okay, they're going to meet each other. They will never meet exactly, so not necessarily in the middle. We're going to find out where is the location of that breakaway point. So they will meet each other, and then they will actually leave each other, because these are two poles. One will go following the first asymptote going up, and the other one will follow the 300 degree asymptote going downwards. Okay, so this is actually they are never going to come close. They will come close each other, never meet each other. They will leave. Okay, so for we're going to find out where is that location of breakaway point, not necessarily in the center. So when they leave each other, they will leave each other 90 degrees perpendicular. So that one is actually step number 7. 90 degrees perpendicular. So I will draw nicely later on. Okay, and then the other one will go down. Okay, so we do not know which one is going up, which one is going down. That's okay. Only thing is that you need to know that the root locus is actually we need to find out the position where it's going to meet each other. All right. Another thing we need to find out is that crossing at our imaginary axis. Okay, so that is going to be the next step number 9. I want to find out the location of the imaginary axis. The cutting at the imaginary axis. But of course, the last pose, don't forget, there's another pose that we follow the 180 degrees. Okay, so because there's only one region of locus there, so it will go from that pose at negative 6 there, and it will go towards 90, towards infinity, following the 180 degrees asymptote. Okay. Okay, step number 6 is to find sigma b, which is your breakaway point. That is given by the 1 over sigma b minus the value of your pole. So you have 1 over sigma b minus 0 plus 1 over sigma b minus 2 plus 1 over sigma b minus 6, and that is actually equals to 1 over minus sigma b minus your poles, okay, and minus your value of your 0. But you don't have 0, so that will be 0 there. Okay, that will be equals to 0. If you have 0, then you have 1 over sigma b minus whatever value of 0 that you have. Okay, so if you have many 0, then you can put there similar like what I did for my poles. Okay, so in this case nothing, so you just put 0. Okay, then you're going to simplify this. You're going to cross multiply, have a common denominator, and then you're going to solve the problem, solve the mathematics for your value of sigma b. Okay, so you're going to use your quadratic equation to find out this. So first we do the cross multiplication and have a common denominator. Okay, sigma b plus 2. these are all then having a common denominator of sigma b plus 2, sigma b plus 6. Okay, but because this is going to be equal with 0, you can see that the denominator will be multiplied with 0, isn't it? That will disappear, the denominator will disappear. Okay, because it's multiplied by 0. So I'm just going to have the numerator, and that numerator will be expand, and then will equate with 0, and we're going to solve the problem later on. The denominator will disappear, So I just expand the equation. So I have then I need to collect all the value of sigma b squared. So I have 3 sigma b squared, and then I have 8 sigma b plus 6 sigma b plus 2. That will be 16 sigma b, and then I have to plus 12 sigma b 12. Okay, that's equals to 0. Okay, so that's 12. So oh, I forgot sigma b. There are 3 sigma b squared, so I put 3 sigma b squared, okay, plus 16 sigma b. Is correct. Let's double check. Okay, and then I have to plus 12. That's equal with 0. Okay, so then I need to solve this sigma b. This is a quadratic equation, so you can use your calculator to solve it. Then you're going to have two value of sigma b. So you need to find out what are the two value of sigma b. Using your calculator, you can solve this, and you can find out that the sigma b is minus 4.43, which is not right, isn't it? Because the poles is in between minus 2 and 0, isn't it? So the position of your breakaway point must be in between 0 and minus 2. So 4 is somewhere there. So minus 4 is not really the value that you are looking for. So the second value of your sigma b is negative 0.902. So that is the one that you're going to use. So the first one will be neglected, because that is not what you are looking for. Okay, so you're going to use 0.906. So that is where your your poles will meet each other, and it will break away at 0.902. So that is your breakaway point. So your poles will leave each other 90 degrees perpendicular to the real axis, and then it will go and follow the asymptote. Okay, so you must on your drawing you must show step 7. Even though we don't write the step 7, you must show that the step 7 is actually poles is leaving each other 90 degrees perpendicular to each other. And you must remember that root locus is a mirror image. So whatever you have on the positive side of your imaginary axis will be a mirror image to your negative part of your imaginary axis. Okay, so that is why your drawing is looking like that. Okay. Okay, you already know the location where it will break away from each other. So then you need to know what is the location when it is crossing your imaginary axis. This is when you are going to have the critical value of your system, where your K will be critically stable at that point where it intersects with your imaginary axis, because anything above the value of K at that point will lead you to unstable region. You can see your root locus is already going towards your unstable region at that location. Okay, so anything more than the value when it's crossing your imaginary axis, it will be the system will be unstable. So to do this, we're going to do step number 9. Step 7, there's nothing I need to calculate. I just can write there that locus will leave your imaginary axis, will leave your imaginary axis, your real axis, perpendicular to each perpendicular to your real axis, which is plus minus 90 degrees of your real axis. That's all. No need to do anything. For this particular example, you do not need to do step number 8, because step number 8 is actually related to your complex poles. In this case, you do not have complex poles. You only have real poles. No complex poles or no complex zero. So if you have any complex pole and complex zero, then you're going to do step number 8. In this case, you don't have any, so I'm not going to do it. Okay, so we just skip first step number 8. I will show you different example to do step that require you to do step number 8. So we're going to skip into step number 9. You already done step number 9 when we learned Root-Hurwitz criterion. So Root-Hurwitz criterion is to find the crossing at your imaginary axis, to find the crossing at imaginary axis where your system is about to become unstable. So your system is initially was a stable system, or maybe it is unstable system pun tak apa. Some example, you have unstable system, but in this case you have a stable system, but then it will cross the imaginary axis and go towards unstable region. So we want to know what is that location of locus when it actually cross the imaginary axis. So exactly at the imaginary axis, it is called critically stable system. The moment it become a little bit more than imaginary axis, a little bit more than the critical system, it become unstable. So that is the region of unstable. So we want to know what is that location of your, we want to know the value of your critical K, critical gain, and then the value of your crossing at the imaginary axis. Okay, that is your step number 9. So I'm going to do root array, and then using our Root-Hurwitz, we will find the value. Okay. Okay, first we need to start with our characteristic equation. So you go back to 1 plus kgh equals to 0. That is your characteristic equation. And then for this example, it is 1 plus k over s plus 2s plus 6. Okay, so this is your characteristic equation. Multiply by 1. I'm not going to write that 1. Okay, equate with 0. Then I need to expand this equation. So if I expand this equation, it will give me s plus 2, s plus 6 multiplied by 1 plus k. Okay, plus k equals to 0. Of course, the denominator will be same. Okay, common denominator will be s plus 2, s plus 6. But because that part, s plus 2, s plus 6 will be multiplied with 0 on our equation here. So that part will be neglected. It becomes 0. So you're going to have your equation will be just s plus 2, s plus 6 plus k. S multiplied by s plus 2 multiplied by s plus 6 plus k equal with 0. So that is your characteristic equation. Using this characteristic equation, we can later then plot our root array. Okay, root array. And then from the root array, we can identify the critical value of k. Okay, so root array later on, if you remember when we did our previous class, Root-Hurwitz criterion, we need to plot root array based on our characteristic equation. So I expand first this equation, and if I have a common parameters for my coefficient, I'm going to then collect it together. So in this case, I don't have any common coefficient. So if I have, for example, 12s plus ks, so I will collect the 12s and ks together. So in this case, not just k, no need to collect together. So for root array, I'm going to start with s cubed, then s squared, and then s and s to the power of 0. Okay, and I will fulfill the first. I will fill the first two row with the coefficient. For s cubed, the coefficient is 1. I'm going to skip 8. I'm going to go to the next one is 12. So s squared, the coefficient is 8. I will skip 12 and go to the next one, which is k. Right, and then for the s to the power of 1, we do the we will do the calculation. I have 8 multiplied by 12 minus k divided by 8. So that will be the one that I'm going to put at s to the power of 1. So we have 8 multiplied by 12 is 96 minus 1 multiplied by k divided by 8. Okay. The next element will be 0 because I have 8 multiplied by 0 minus 1 multiplied by 0. So that will definitely give me 0, okay? Then for the bottom one, I will just have k. How do I know that? Because it's 96 minus k divided by 8 multiplied by k and then minus 0. 8 multiplied by 0 is 0. So that will give me the value when we have whatever it is multiplied by k, divide again by that number. So that's going to give me k. Okay, so that is my root array. So for my system to be stable, the root array, the first column must be all having the same sign. So either it's all positive or all negative. So in this case, the first two is already positive. For the system to be stable, then the the third terms and the fourth term must also be positive. But in this case, I'm not going to look for system that is stable. Okay, because the first two is already stable, so the third and the fourth must also be stable to have the same value. Okay, so in this case, I want to know if the system is critically stable. Okay, that point is critically stable. Okay, and I want to know what happened when the system is unstable. Okay, so for critically stable, I want to know that magnitude 2 here must be equals to 0. So it's not either it is positive like when it's stable, and then these two must also be positive, then it's stable. But in this case, we want it to be critically stable. So these two elements must be equal to 0, because to find the point where it is actually critically stable. Alright, so when we going to put the value become these two elements, we need to equate it with 0. So if I have the first one, when I have k equals to 0, that will not give me my point that I'm looking at. So when I have k equals to 0, that will be a point where because the system is already started, the position is already in middle of a root locus. So in the middle of the root locus, k cannot be 0, because we know root locus started when k equals to 0, and it start to increase the value of k from 0 to infinity. So at that point, k cannot be 0 at that point. So that point must have value. It cannot be suddenly in the middle of the locus, k equals to 0, because it start at k equals to 0. So the value that we found just now, when k equals 0, must reflect the value of your poles that you have here. You see, you have poles at your imaginary axis here, isn't it? So that is when the k equals to 0, not when you cross your imaginary axis here. Okay, so that is what we're going to find out. What happened when it crossed the imaginary axis? So we're going to look at the second element that you have just now. So 96 minus k divided by 8. So that will definitely be the location, the point that you want to have. So when k equals to 0, the first point here is actually the starting point. Okay, when you have your poles there. Right? So that is also in the imaginary axis. So your poles must be reflecting this value of k equals to 0. So the second element must be coming from 96 minus k divided by 8. So if I look at this, 96 divided by minus k divided by 8. So 96, k is equals to 96, because 8 multiplied by 0 is 0. So k is equals to 96. So when k equals to 96, this is the critical value of k. Okay, when it crosses the imaginary axis, your k is about to become unstable, so we call it critical k. So it's going to be unstable at that value onwards. So if you have anything more than that, your k will be 0. Okay, your system will be unstable. So this is the critical value of k, 96. So anything above 96, when you put your controller there in your system, that value of k you start with maybe k equals to 1, and you increase it to infinity. But when your k reaching 96, that will be the point where your system will become critically stable. Anything above that, 96.1 for example, or 96.5 for example, your system will become unstable. Anything be above the critical value of k is when you're going to have unstable region. But not only that you want to know the critical value of k, you want to know what is that location, the position of your locus when it cross this critical value. You want to know that coordinate. Okay, so using this root array, we can also find the coordinate. So if I use this root array again, if I look at the S squared quadrant, okay, so this S squared, actually if I know the value of critical value of K, I can substitute this critical value of K straight away in my characteristic equation. But at the same time, I can also use this one. If I substitute the magnitude of value, critical value of K in the characteristic equation, I can also find the position of roots where it cross the imaginary axis, but there will be quadratic equation, so there will be 3 roots if I put in the characteristic equation. In this case, this quadratic equation, quadratic plus cube equation, so it will produce 3 locations of coordinate. Okay, so one will be one, just any one coordinate. The other 2 will be the conjugate and the complex and conjugate. So that complex and conjugate is the one we are looking for. Okay, so I can use characteristic equation. But another way, a simpler way, is for me to use my root array, and I'm gonna replace it in this S squared part. Okay, so when in this S squared, I can have it as written as 8S squared plus KS. Not KS, sorry, K, because the coefficient of K is as 0, isn't it? So I have 8S squared plus K, I equate that with 0, and then I can substitute the magnitude of K equals to 96 into this equation. Okay, then I will solve for my S squared. Then I will solve for my S, and then that S will give me plus minus because it's quadratic, so it will give a plus minus. Before that, just to show you that it's going to give me negative 96 over 8. So negative 96 ni, if you remember J is, if I take square root of negative, so it will give me a value of J, kan? Sebab J is a square root of minus 1, isn't it? If you remember, J is equals to square root of minus 1. So I can replace that minus part with a J. So that S squared, if I take S squared, if I want to square root the minus value, so I can just add the magnitude, the J there. So then I will just take the square root of the positive part, 96 over 8J. Okay, so 96 over 8 is 12. 12 square root is going to give me value of 3 point something. Let me calculate that. So that is giving us plus minus 3.46J. So this is a complex and conjugate, because you remember root locus is a mirror image about the real axis. So therefore, if I have a 3.4J for the crossing at the positive part, it will give me the negative 3.4J at the negative at the other part. Okay, so if I redraw this, because this one just now we estimated wrongly, so we need to redraw this again. So if I actually redraw this, I will see that the angle of asymptote is have to be slightly bigger. You need to use protector to measure this. So I have a pulse leaving my one of the poles going towards the asymptote, and it will cross positive 3.46J at the positive part of my imaginary axis, and the other one will go and cross the negative 3.46J. Okay, I have to make sure it follow asymptote. Cannot go going away from asymptote, must follow asymptote. So that is the other locus that I have. Okay, so these are the two locus. Just make sure that when it leave each other, the location is according to your sigma b, and then once it have leave each other 90 degrees perpendicular to the real axis, it will then follow your position where you cross your imaginary axis. At that point, your K is equals to 96. Both top and bottom, the magnitude of K is 96, but the coordinate of your locus will be, at that point, will be, coordinate of your roots will be 3.46 positive and negative 3.46J at your imaginary axis. So these are the locations of your critical values. Okay, so at anything above this value, your system will become unstable. Anything above this value. Okay, so when you plot your imaginary and real axis, you must make sure you're plotting using same scale. When you plot using same scale, then only then you can use it to assess the stability of the system. Okay, so that is the sketching for our root locus. So next, what I'm going to show you is we're going to actually use this root locus to assess the stability of the system. Okay, before that, maybe I will show you another example later on in different video on how to use example with complex and conjugate poles. Okay, thank you very much.